Hello and welcome again to Let's Talk Advanced Chemistry. Let's Talk Chem 2 with Pastor Dan. We are going to do with enthalpy. We're going to do a little review on concepts we covered before. This is the easier concept, the one that I'm always flipping back and forth. We're going to come back to Hess's law. We talked about something called Gibbs free energy and entropy. So don't get too comfortable getting away from that. We're going to come back to it. But right now, let's go back and define again thermochemistry, a different definition. Thermochemistry defined as a steady reaction process, a result in the release absorption of energy. Now, energy's ability to do work, so the delta change in energy is equal to the Q, the enthalpy, plus work. So you put the work you do plus the enthalpy, that gives us the energy we do. Now remember, there are two types of energy that do exist. This is the basic here, kinetic and potential. The way we would do if we were to calculate it, KE, kinetic energy, is 1/2 the mass of substance times the velocity of it squared. Should look an awful lot. E equals mc squared because it's a equal process here. And then potential energy, gravitational potential is equal to mass times gravity, which on Earth is 9.8 meters per second squared, times the height that the object is at. All right, now, enthalpy itself, we talked about before, has two different values. It's the energy associated with the movement of heat. It can either be delta H, which we talked about for capacity and specific heat, or it can be Q, and we'll use Q more in Chem 2. Delta H is more Chem 1 kind of concept. Now, in terms of enthalpy reaction, energy can absorb or release energy. If I have a delta H of negative, that means that it's exothermic, and again, that means it's releasing energy, exiting. If it's positive, that means it's absorbing energy. Okay, so if the value itself is negative, there's no such thing as negative energy. We just write that to express that it's releasing energy, it's coming out of the system. If it's positive, that means it requires energy to start the process up, or it's going to get cold. One of the two things. All right, so look at the problem here. Determine the energy released as 35.988 grams of methane is burned if the enthalpy of the reaction is negative 67.977 kilojoules per mole. Now, we're going to always start with reaction. And even if we don't need to, and I'll explain why, just so we get in the habit of doing it. So here we have the reaction methane burn is combustion. So we have methane CH4 plus O2, and the products of combustion reaction is always CO2 and H2O. Balancing it up, we get 2 for oxygen and 2 for the water. Now we're not going to use the enthalpy here. We'll use the value that we have right there. So, and the reason we want to do that, this is going to be a unit converter. That's negative 67.977 kilojoules per mole. So we take our value and we put it over 1. Now, in order to get into moles, we need atomic mass, formula mass, molecular weight, or we need molar volume, 22.4 liters of a gas. We talked about that before, stoichiometry. Carbon's 12, hydrogen is 1, times 4 is 4. Again, I round to whole numbers with the exception of copper and chlorine. So we have 16 grams of CH4 is 1 mole. Now, from the problem, it says that negative 67.977 kilojoules is in every 1 mole. So we just put that in there. We don't really need the balance equation, but it's good to have there so we see the process, and we will have to have ones later. All right, so take our handy dandy, well, just make sure everything crosses out, grams cross out, moles cross out, we're in kilojoules. So take our handy dandy Joe Dandy calculator, 35.988 times 67 equal, divide by 16 equal, we're going to get 150.74 kilojoules. Remember, this value is negative, which means it's exothermic. Or we can also say, if we don't want to make it negative because some people don't like it because it's hard to get your mind around a negative value, we could say that 150.74 kilojoules of energy is released. All right, first problem. Let's try another one. That's our answer. Let's try another one. Calculate energy needed to initiate a reaction of 45.77 grams of ammonium nitrate with barium hydroxide if the delta H is 10.225 kilojoules per mole. And you see that's positive, which means that it's endothermic, and this is going to get cold. And we talked about that in Chem 1. That is smelling salts. It actually, or our heat pack, involved with that. So reaction there is actually it's a cold pack, not a heat pack. 4NO3 plus BaOH twice gives BaNO3 twice plus NH4OH. And balance at the reaction, we put 2 NH4NO3 and 2 NH4OH. All right, now we're going to get and start with the 45.77 grams of ammonium nitrate, and that's over 1. Nitrogen's 14, that's times 2. There's 2 of them there, so that's 28. Hydrogen 1 times 4, 14. Oxygen 16 times 3, 48. 48, 4, 28 gives us 80 grams of NH4. Now again, I'm giving it per mole, so we actually don't need the reaction here. So we just put the value like that, 10.225 kilojoules per 1. I just noticed in the last problem I didn't have the rest of it. I apologize there. You do have to have the entire number as it's in the problem. Because as I tell you, take your calculator, 45.77 times 10.225 equal, divide by 80. My grams cross out, my moles cross out. We get 5.850. Remember for sig figs, I have 4 sig figs here, 4 sig figs here. That zero's after a number, after zero, after decimal. It's showing exactness, has to be there. We could also say that it's positive, means it's endothermic, or it's absorbing energy. Either of those is correct. Those are our answers. Now there's another way you can also do that. We can do this in reverse. So we can ask what mass of sodium oxide is synthesized if 25.78 kilojoules of energy is measured and the enthalpy reaction is 765.88 kilojoules. Now we're starting with energy this time. So we're going to go the opposite way. And you see here it's not per mole. So this one, we do actually need the reaction. So we have sodium oxide synthesized. We always go from the elements. So we're going to have Na plus O2 is Na2O, and balancing it up, we're going to put a 4 in front of the Na and a 2 in front of the Na2O. Start with our energy, 25.78 kilojoules over 1. Now from the problem, it tells us it's 765.88 kilojoules, and it's in 2 moles. And the reason for that is we have 2 moles of Na2. There is no per mole here, so we have to go to the problem. Right there we have 2, so we have to put a 2 here from the reaction. All right, and then we want mass, so sodium is 23 times 2 is 46, plus oxygen 16, 16 plus 26 is 62 grams of Na2O is in 1 mole. So take our calculator, 25.78 times 2 times 62 equal, divide by 765.88. Kilojoules cross out, moles cross out. We're in grams, that's what we want. We're going to get 4.174. Again, 4 sig figs here, 5 sig figs, infinite because it's a value that we derived, so we should only have 4 sig figs. Our answer, 4.174 grams is our answer. All right, let's try one more, and I think I'm going to have you do this on your own. So pause the video. Again, I'm not saying per mole here, so you're going to have to do the balanced equation. We're starting with mass, so we're going to go from mass to moles, and then moles to energy, and then if the endothermic or exothermic, energy produced is exothermic. Pause it, give it a shot. You make sure you take the time, work it through, think about the reaction. If you have any questions, email me, ltswpd@gmail.com, or you can make sure you subscribe, like, share, all those kinds of good things. All right, there we go. For the balanced equation, it's 1 mole. So the answer here, check your answer out, should be the 30.40 kilojoules of energy released, or negative 30.40 kilojoules. All right, that's it. Take care. God bless. Bye.